Looking at the orbital angular momentum that we saw from the solution for the Schrödinger equation, we can look at the vector components. We saw that the magnitude of L, the angular momentum, was quantized, as is the Z component. So the diagram on the bottom shows for different L values the vector. And if we just choose one of those, we see that with this angle theta relative to the z-axis, then you have this angle of cosine of theta is adjacent over hypotenuse, so that's the z component over the magnitude, L. And we saw that Lz was the this quantum number ml times h bar, and the magnitude was a different quantum number, L times L plus 1, and then that's multiplied by h bar. So the h bars cancel. They already look like it canceled because they've got a bar through them, but this then gives you ml over the square root of L times L plus 1. All right. So what's the significance of that? Well, when you look at what the possible values are of these two quantum numbers, you see that you can never get an angle of theta is equal to 0. So this, as shown in the diagram, the components make it such that the angular momentum is always at an angle from the z-axis. And also, again, these are quantized numbers, so it's only going to be in steps, which is shown here for these different values of m. All right, and in fact, what's shown in that diagram is for the little l is equal to 2 case. So if we think more about what is angular momentum, we have this idea of a circle that the electron is orbiting around, and using the right-hand rule, if you curl your fingers in the direction of motion, then your thumb points up along the angular momentum vector. And the interesting thing is that this is a charged particle, the electron, and so its motion is creating a current loop. And we can figure out what that current I is by thinking about the charge per time, and for this electron to make one full revolution is the period. And so we have the period of rotation around this orbit. So the period of the orbit is it's the circumference divided by the speed, because that is the orbital speed. All right, and then if we say that the current is this charge per period, then we can write this out as EV divided by 2 pi r. Okay, now why do we do that? Well, if there is this loop of current, that will create a magnetic moment, mu. And so the magnetic moment, mu, is, because they're perpendicular, it's just I times A, where A is the circular area. So we can substitute in what that is. I was EV over 2 pi r, and the area is pi r squared for that orbit. And so we have some things cancel, the pi's cancel at least, one of the r's cancels. So that ends up becoming 1/2 EVR. Okay, so if we now want to write that in terms of capital L, which is the angular momentum, so you remember in this simple circular case that for one particle, L is equal to mvr, the mass of the particle, times its velocity times the radial distance, then you see that all we would need to do is L divided by m is equal to VR, and substitute that in. So you get E over 2m multiplied by capital L, which is this angular momentum. So when we've got that, we can now insert the quantized values that we got as shown above when we were looking at the cosine of the angle. So if we do that, we get E divided by 2m multiplied by square root of L times L plus 1 multiplied by h bar. Now, h bar is a constant, so if we want to define a new constant value, which is called the Bohr magneton, so I'll write that down here. That is, mu b is that E times h bar divided by 2m, and then this, you bring that out, and you get this relationship for the quantum number L multiplied by mu b. Okay, so this is the magnetic moment that we see, and this is it's shown down in the diagram as the vector, and it also follows a right-hand rule where this is now, if your 4 of your fingers wrap around the direction of the current I, then your thumb points down in the direction of the magnetic moment mu, which is shown in that diagram, which you see because the current flows in the opposite direction of the motion of the electron, then the mu is pointing in the opposite direction of the angular momentum vector. And if we're looking at the z component, then we can simply say that if we have this relationship here between mu and L, so if we saw that Lz was in terms of this quantum number m, then we can relate mu z, the z component of this moment, is equal to minus ml times mu b, where b is this constant, the Bohr magneton. Okay, and the negative sign is just saying that this is in the opposite direction of a positive z, right? So, good. From this, we're going to look at an example.